So last time we were talking about collisions, but we talked about collisions in one dimension. Today we're going to talk about two-dimensional collisions. We aren't going to go as far as three-dimensional collisions because they don't really add much. So once we've got a collision in two dimensions, we have to define something that we call the contact plane, right? And so this is the plane that is parallel to the two surfaces of contact of the colliding objects, right? So, for example, if we've got two snooker balls or pool balls coming in and bouncing off each other, then the point of contact between the two balls will be a tangent to the surface of the sphere of both of the balls, and that plane where they touch is what we call the collision plane, right? And it's parallel to the planes of contact, right? So obviously, you know, we could have had the ball coming in here, and if it had hit the ball here, then of course we'd have had a collision plane that's along here. So that's the first thing to do, is we have to define what we call the collision plane, and that's the plane parallel to the surfaces of contact of the two objects. Oops. There we go. So what we have here is this is the collision plane. So the first question is we've got a collision, we've got an impulse. What direction does the impulse act with respect to the collision plane? Is it parallel to the collision plane, so along it? Is it perpendicular to the collision plane? Is it parallel to the first object's velocity, so along here? Or is it parallel to the second object's velocity, so along here? Or is it none of the above, right? So somewhere that's not one of those directions. Whoa, okay, so we've got a three-way tie between A, B, and E. Okay, so turn to your neighbor and convince them that you've got the right answer. Okay, let's vote again and see what we've got. Okay, so now we seem to have a favorite now, which is B. So I will show you the right answer, and I will tell you why it's right. So B is indeed the right answer, right? The impulse acts perpendicular to the collision plane. So why is that? Well, if you have a look at what's going on here, right? We've got, so here's our collision plane, and I'm going to ignore the ball below the collision plane. Because if you take the because the impulse is going to be acting on one of the balls, and so we're just going to worry about the impulse acting on one of the balls. So what happens is we've got a ball that's coming in here, and it follows a trajectory something like that, where these angles are not necessarily equal. Right? So if we look at the impulse that's acted on this ball, we have to remember that impulse, first of all, is a vector, so it does have a direction, and it's equal to the change in momentum of the ball, right? So clearly, if we look at this, we can split the momentum up into two components, and we've got a momentum that's perpendicular, and we've got a momentum that's parallel to the collision plane. And when we look at this, right, at the point of contact here, this ball is just touching the surface of the ball beneath it. And so we have a contact interaction, a normal force, that's effectively what's giving us the impulse. And that normal force is going to be perpendicular to the surface of contact. Now, of course, it's varying, it's not constant, it's a dynamic situation, it's not like a block resting on a table or a slope or something. So we have a dynamic normal force, but nevertheless we have a normal force, and that collision is going to cause that normal force now to generate an impulse that is perpendicular to the plane of the collision. And the result is that the impulse is also going to be perpendicular, and you can tell that there's going to be a perpendicular impulse by looking at the momentum, because clearly the momentum here, well, you can't necessarily tell by looking at the diagram that the parallel component of the momentum has changed, but you know for a fact that the perpendicular momentum has changed, because initially it was going down and now it's going up. So there has to have been at least a component of the impulse that has acted perpendicular to the plane of contact. And then if you think about what causes the impulse, it's this normal force, and so therefore the normal force acts perpendicular to the plane of contact, and that's what actually generates the impulse. So the impulse is perpendicular to this collision plane, which goes through where the two objects touch, right? So we can actually use this, and we will be using this to help solve problems when we deal with these two-dimensional collisions. So this has answered this one, actually. So since we've got an impulse now acting perpendicular to the plane here, right, and we said that impulse is change in momentum, then what, of course, this immediately implies is that perpendicular to the plane, there has to have been a change in momentum. But if there's no impulse parallel to the plane, that means there's no change in momentum parallel to the collision plane. And that is what we are going to use to solve these problems, that the momentum of each ball independently, parallel to the collision plane, does not change. And the reason for that is because there is no impulse acting parallel to the collision plane, so there is no change in momentum parallel in that direction. Okay, so next question. So, okay, no, that's the same thing, right? Okay, we'll skip over those. There's repeating what I've already said. So what we're going to do to solve this is we resolve it into these different components of momentum, and we take the perpendicular and parallel components of the momentum with respect to the plane of the collision. And we choose this plane of the collision, although I talked about it being the contact surface, the actual definition of the collision plane is the surface that is perpendicular, the plane that is perpendicular to the impulse that acts on the balls, right? So the impulse that's acting here clearly has a net direction. So if we go parallel to the plane of the collision, since the mass of the ball does not change during the collision, what it means is that the component of the velocity parallel to the collision plane is going to be equal to the component of the velocity parallel to the collision plane after the collision, right? Because this is the component, you can imagine putting an m in here, and then it would be the component of momentum, right? But since m is constant, you can cancel it out. And the same goes for the second ball, that the components of the velocity parallel to the collision plane are going to be the same. Now, this doesn't mean that these angles here are going to be the same, because the perpendicular component, of course, changes. And these angles depend on both the parallel and the perpendicular component, right? So we split it up into these components, parallel and perpendicular. Now, when we resolve the components, so we've solved it now in the parallel direction, that's easy. The components of the velocity and momentum remain the same. But if we do it perpendicular to the collision plane, then at this point now, we've reduced it back to a one-dimensional collision. We have some initial velocity coming in from both of these balls, and then we have some final velocity going out. Now, okay, we have some angle to resolve the components perpendicular to the plane of the collision, but this is exactly the same type of problem that we did in the last lecture with the, the head of the golf club and the ball, or the train and the trucks. So again, we have exactly the same type of collision perpendicular to the collision plane. We just have a one-dimensional collision, and we have a coefficient of restitution, right? Because again, we can have different types of collision, one where the two objects end up together afterwards, and ones where they separate afterwards. So again, we end up with our conservation constant momentum expression here, where we just multiply these velocities here by masses to turn them into momentum, and we do it just the same as we did before. Okay, so let's actually work through an example. So what we've got here is we've got, we're going to do curling. So we've got curling stones sliding on ice, which are nice, undergo nice collisions, and friction's minimal because we're doing it on ice. So what we're going to assume here is that we've got a stone, and it's launched traveling at 2 meters per second when it collides with another stationary stone at an angle of 45 degrees. So when you see that in a question, it says at an angle of 45 degrees, what it's telling you is that the plane of the collision is at 45 degrees to the direction of motion of the stone, right? So it's a glancing collision. It's not head-on now. It's a glancing collision. It's going to be two-dimensional. So if the collision is perfectly elastic, so that tells us that our coefficient of restitution is 1, and the stones have equal masses, so we've got equal masses here, what are the final speeds of the stones, and what is the direction of their velocities relative to the velocity of the first stone? Right, so we've got two objects now, equal masses, 45-degree collision. So the first thing, as always, is we want to draw a diagram. So what we've got is we've got our curling stone coming in at 45 degrees. And we have the plane of our collision here. And so this angle here is 45 degrees. And at this point, it collides with another stone that's sitting here, right? And this stone moves off with some velocity. And this original stone that comes in also moves off with some velocity, right? So we'll call this angle theta 1 prime and this angle theta 2 prime because we don't know what they are. And this one will be V1 prime and this will be V2 prime. Oops, it's not squared, primed. Because we don't know what they are, right? So we just give them labels and stick them in there. So first thing we can do is we can look at what happens parallel to the collision plane. Now, parallel to the collision plane, there's no impulse. Remember, we said the impulse acts perpendicular. So if we're looking parallel to this collision plane, there's no force, no impulse, momentum is constant for each stone individually, right? Now we're taking each stone separately. The momentum has to remain constant parallel to the collision plane. Well, if we look at this second stone, it's initially at rest. So it has no momentum parallel to the collision plane. And so after the collision, it's also going to have no momentum parallel to the collision plane. And the only way we can make that happen is to make this velocity 90 degrees. Right? So theta 2 here is equal to 90 degrees, and we can draw this in. We still don't know what the value of it is, but we do know the direction now is at 90 degrees to the collision plane. Right? So we've at least all answered part of the question now, because that's the only way we can make the momentum parallel to the collision plane 0 afterwards. So if we look at this stone coming in here, if this is our initial velocity v1, then we can do conservation, constant momentum parallel to the collision. So the change in momentum of the first stone will equal 0 parallel to the collision plane. And so what that's going to tell us is that mv1 cos 45 degrees is because the initial momentum is going to be equal to mv1 prime cosine theta 1 prime, right? So that tells us that for the first stone, we end up with this constant momentum parallel, and we can divide through by the masses. And so that was what I was talking about before. You end up with the initial component of velocity is equal to the final component of the velocity parallel to the collision plane. So we've learnt something from looking parallel to the collision plane. So if we look, now what we want to do is we want to look perpendicular to the collision plane. And in this case, we've reduced everything to a one-dimensional problem. So I'll draw this back out now as a one-dimensional problem, perpendicular. So this is perpendicular to the plane. And what we end up with is this is V1, sine 45, right? So that's the perpendicular component of the velocity here. And this one, of course, is 0. And after the collision, this has a component V2 prime, because we know it's perpendicular already. And this one has a component V1 prime sine theta 1 prime, right? So that's now our one-dimensional collision. So if we use constant momentum, right, the total momentum of the system is going to be, put the right arrow in here, the total momentum of the system is going to be 0, so it's going to be constant, sorry, not 0. So the initial momentum is m, the mass of the stone. So both of these stones, of course, have mass m, right? So it's going to be the mass of the stone times v1 sine 45 degrees. And that is going to be equal to, this arrow is in the opposite direction, so I have to put a minus sign in here, minus m v1 prime sine theta 1 prime plus m v2 prime. So the m's cancel, and again, we've got an expression in terms of the components of velocities. And so that's our constant momentum. Now what I'm going to do, so on the notes, I did constant energy because it's an elastic collision. Here, what I'm going to do is I'm going to use coefficient of restitution, right? So you remember we had our coefficient of restitution was defined as the relative velocity of separation divided by the relative velocity of approach, right? Now here, of course, I've got to use the components, and this was going to be equal to 1 for an elastic collision. So what I have, if I look at the components, here I have v2 prime, and I have to subtract off v1 prime, but this is negative, so it's going to be minus v1 prime sine theta 1 prime, and that is going to be equal to v1, keep on writing cosine, sine 45 degrees, right? So if I write this out, what I'm going to end up with is that v2 prime is equal to v1 sine 45 degrees minus v1 prime sine theta 1 prime. Right, so that's what I get for the coefficient of restitution. And if I look at this one here, I get v2 prime is equal to v1 sine 45 degrees plus v1 prime sine theta 1 prime. So there's only one way I can make both of these equations be correct. Well, okay, there's two ways. I can either make the final velocity of v1 0, so it stops, right, because then this would be 0. But if we look back at this equation, if I make v1 prime 0, I'm also going to have to make my initial velocity 0, which means the thing isn't moving and there isn't going to be a collision, right? And in fact, having the initial velocity 0 would be at odds with the initial conditions where we're told it's moving at 2 meters per second. So I can't set v1 prime equal to 0. So the only other way I can do this is to say that sine theta 1 prime, so this means that sine theta 1 prime is equal to 0, because the only way I can make this term be 0 and both these equations be true is by having sine theta 1 prime is 0. The only way I can make sine theta 1 prime is 0 is if theta 1 prime itself is equal to 0, right? And so therefore, what I've just shown is that this angle here is 0. So this stone actually moves off along the collision plane. It has no component of velocity perpendicular to the collision plane. So now, if I draw the diagram, what I've done is I've managed to make it a lot simpler. So here's the collision plane. And this comes in at an angle of 45 degrees, and it goes out at an angle of 0 degrees. And this moves vertically off, well, perpendicular to the collision plane, with its velocity. And so now, if I look at the equations I had, what I've got is I've still got my, from the change in momentum for the first ball parallel to the collision plane, I have V1 cosine 45 degrees is equal to V1 prime cosine theta 1 prime. And this, of course, is equal to 1, because theta 1 is 0, theta 1 prime is 0. So I have V1 prime is equal to V1 cos 45 degrees. So now I know my final velocity and I know the direction of the first stone. And then if you look at these two equations here, we've just shown that this term is 0. So I know that V2 prime is V1 sine 45. And so at that point, I've now solved the question. All I have to do now is say that V1 is equal to 2 meters per second. Cosine of 45 degrees is 2 over root 2, or 1 over root 2. And so what I end up with is that V1 prime is actually equal to V2 prime, and it's equal to 2 over root 2 meters per second. So that's what, 0.707 meters per second, something like that. I think we've got the answer here. Yeah, okay. Sorry, no, not 0.0707. It's, oh, 2 over root 2, of course. What am I doing? Yeah, silly me. 0.707 is 1 over root 2, not 2 over root 2. So both velocities are root 2 meters per second, and that's what happens in the collision. One moves off parallel to the collision plane, and one moves off perpendicular. Now again, what I hope you can get from this is I did it deliberately slightly differently from what's in the notes, so that you can see that using the coefficient of restitution, I mean, here in the notes I had lots of equations, lots of algebra, lots of velocity squareds and so on like this. You can do that, only remember, you can only do that for an elastic collision, where the coefficient of restitution is 1. But what I hope I'm showing you is that this using the coefficient of restitution makes the maths for these types of problems an order of magnitude easier, right? It's far, far less algebra, because what you always find with these questions is you're expanding square brackets. You get these hideously long expressions. Half the terms in those expressions add together and condense down, and then you end up with a term that you've got to factorize, because you can always factorize it, and you factorize it and you end up with something simple at the end. But if you use coefficient of restitution, it avoids having to add all these squared signs, right? So the choice is yours, how you do it how you like, but I'm pretty certain has anybody seen coefficient of restitution before this course? No, right? Because I'm pretty certain that they don't teach that in the schools, but I think it makes these types of problems really a lot simpler from the maths point of view. You do have to think a little bit when you're setting it up to make sure you get the relative velocities correct, but then it makes the maths afterwards a lot easier than trying to use conservation of energy. But conservation of energy works, and you're free to use any method you like that works and is physically valid in an exam. So if you really want to use conservation of energy, by all means do it. I just think that it'll take you longer, and it's more error prone when you're doing that much algebra. But you're free to choose whatever method you're most comfortable with. Okay, any questions on that? Good, excellent. Okay, so What we've shown now is we've got two-dimensional collisions. We've got momentum is constant in these collisions as well. And in fact, conservation of momentum can actually be an extremely useful tool even when you're doing fundamental physics, right? So cutting-edge research today uses the fact that momentum is constant, and we can use it to detect particles. So when we're doing collisions in particle accelerators, we can produce many different types of particles, and one of the types of particles that we know we can produce are things called neutrinos. Now, these are very strange things. They are almost have no mass. We now know that they do. The mass is so small, we don't actually know what the mass is, but we know that it's not zero because of the fact that they sort of oscillate and they can change their type. So we know that they have a mass, but it's so small we don't know what it is. And they have no electric charge, which means that they can pass through huge amounts of matter. So, for example, one of my colleagues here in the department works on works at the South Pole, where they've sunk, they literally melt holes into the ice and put photomultipliers, so light detectors in the ice. And what they detect is they detect particles produced by neutrinos that have passed all the way through the Earth and are coming up from the ground underneath ice that's about 7 kilometers thick. And they can detect the little flashes of light that the particles produce. For the few, there's the tiny, tiny handful that actually interact in this massive cubic kilometer of ice that the instrument. So neutrinos can pass through actually light years of material before you've got an actual serious chance of them interacting. Which means that actually they're relatively safe particles because, of course, there's in fact thousands of them left over from the Big Bang passing through your body every second, and of course none of them interact, and so it's not dangerous, but in fact we can't confirm that they're there because they're so hard to detect. So when we smash these, so what we do in particle colliders is we smash these subatomic particles together, and as we see when we'll do relativity, that has a lot of energy, and that energy we can turn into mass and create new types of particles. And so if we take what's now the second highest energy accelerator in the world, the Tevatron Collider at Fermilab, they collide protons and antiprotons, so that's an antimatter proton, at energies of about 2 tera-electron volts. So an electron volt, 1 electron volt is the energy that an electron gets when you accelerate it through a potential of 1 volt, and tera is 10 to the 12. So it's 2 trillion electron volts. It's about a microjoule in everyday units. And we can convert these, so these are the momentum of the particles, which we can also use in these strange units, but we can convert these into kilogram meters per second, right? So we have momentum, equal and opposite momenta coming in, and so what we know is that the total momentum of this collision here is 0, right? We know that we have 0 momentum before the collision because they have equal and opposite momenta. And so this is just a picture of it. So there's a whole series of accelerators accelerating the particles up. And then this thing here, the main injector, is what we also use to make the antiprotons, because we can't go out into nature and find clumps of antimatter sitting around. So we actually have to make it in the collider and collect it and then inject it in. And so this is the picture in real life. So if the initial momentum before the collision is 0, just as all the stuff we've been doing here, all the examples we've talked about here, if we have 0 initial momentum, the fact that the momentum's constant means that the final momentum of the collision is 0, too. So what we do is we have our detector built around the point where these particles collide. We see the particles that are produced in the collision, sort of like the debris from a car accident, go shooting out into the detector, and we can measure the momentum of all of these particles, at least all the particles that we can see. The problem is if we've got something like a neutrino that can pass through the entire planet without interacting, it's certainly not going to have a problem passing through our detector without interacting. And so we've got a problem is how do we know that we've produced a neutrino? And what we do is we use constant, the fact that the initial momentum was 0, because the final momentum also has to be 0, and so we can add up the momentum of all the particles that we can see, and that should give us 0 within experimental uncertainty. And when we get an answer that's not 0, that tells us that we've produced a neutrino, or at least produced a particle that we can't see. And so this is a picture of the detector. The collision happens here, and as you can see, the whole detector sits around this interaction point, so we can see all the particles that are produced. And this is the typical sort of picture. So we produce something called a Z boson, and it decays into 2 electrons. And you can see the electrons go out back to back, because this guy is produced almost at rest. It's a very heavy particle, so it's produced almost at rest. And this is sort of noise and spurious things. We won't go into what those are. But you can see that these electrons here are produced almost back to back, conserving momentum, right? And the reason they're produced back to back is because of conservation of momentum. And so if we produce something, so this is a rather busier event, it's something called a top quark. There's 2 of them that are produced, and what happens is one of them is decayed and produced a neutrino, and the neutrino has headed out in this direction here. And so what you see is we total up all the momentum of the particles that we can see, and we're left with this missing momentum over here. And so that tells us that there's a particle that we can't see that's shot off in this direction. And in fact, this is how neutrinos were first thought of by theorists, because they looked at nuclear decays. Neutrinos are also produced in nuclear beta decay, and they had a problem that conservation of energy and momentum were not being observed in beta decays, because they had a nucleus that would kick out an electron, and the electron energy would vary. And if you've got a 2-body decay, you can't have a varying energy. You always have to have the same energy every single time. And so the fact that you get a varying energy meant that you weren't conserving energy. And so the solution to that was, rather than rewrite the fundamental structure of space-time, they said, well, what about an extra particle being produced? And so, in fact, and then several years later, they actually detected it, and the guy who detected the neutrinos for the first time won a Nobel Prize. So this is the interesting bit, though, where we get to the cutting-edge research, is that neutrinos are not the only thing. We have a problem with the universe in that 95% of it is missing, and we don't know what it is. So all of the physics that you've done so far, in fact, all of the science of any description that you've done, it concerns about 4.6% of the universe, and we've got 95% of the universe out there that's made up of stuff that we don't understand, and 23% of it is made up of this stuff called dark matter that's not got an electric charge and has a gravitational field, and that's all we know about it. We don't know anything else about it at all other than that it's out there. And so what we're doing is we're trying to be able to produce that in these particle colliders, and because it's neutral, weakly interacting, we will not actually see it in the detector, and what we will detect it using, if we produce it, is missing momentum. And so this is an event, it's now quite a few years old, but this was an analysis I was doing on D0, and we got one candidate event. Unfortunately, if you look at the chances of the known physics producing an event like this just due to experimental inaccuracies in measurement, then you expect to see one event like this, and we saw one event like this. So it's not evidence for dark matter, but this is what a dark matter event might actually look like, where you've got some electrons produced over here, or muons, sorry, produced over here, and you have a large amount this time of missing momentum because the dark matter particles got a lot of mass. So conservation of momentum, we can actually use it to detect the existence of the missing 23% of the universe. The other stuff's dark energy, and even the theorists don't have a clue as to what that is. So we've still got a bit of work cut out for us in physics. Okay, so next topic we're going to cover is something called the center of mass. And we're going to come back to this later on when we start talking about rigid body rotations as well. It's important there. So the way you can sort of think of the center of mass is it's the average location of all the mass in an object, right? So you were going to say all the mass of an object is located at one point, this would be the center of mass. And so what we do is we imagine that the object is a collection of point masses. So obviously when we're doing this, if you've got a solid object, if you're going to start breaking it down into point masses, that immediately implies we're going to be using calculus to calculate it, because you've got to have infinitesimally small point masses, and if you've got a rigid body, it's a problem. But for the moment, we'll just concern ourselves with point masses. So imagine we've got a system of point masses. Then the position of the center of mass is basically a weighted a sum of the positions of the particles. So Ri here is the position of a particle, weighted by the mass of each particle, and then we divide that by the total mass of all the particles. So what we're doing here is, if we imagine we've got some system of particles here, right, and this is M1, M2, M3, M4. Each of these has some position vector associated with them, R4 in this case. And so the position of the center of mass, in this case, the position vector of the center of mass would be the sum of the position vectors of each of these particles weighted by the mass. And so that, of course, it means that if the mass of M1 is 100 times the mass of M4, then the center of mass should be a lot nearer to M1 than it will be to M4. And that's why we weight it by the center of mass. So what you'd end up in this case is M1 times R1 plus M2 R2 plus M3 R3 plus M4 R4, right, where this is a vector sum. Each of these now vectors has components, and we divide that by the sum of the masses. Right, and that would give us the position vector of the center of mass. And you can tell we're going to get a position vector because each of these quantities is a mass times a position vector, and we're dividing it by a mass, right? So dimensionally, kilograms will cancel out, and you'll be left with a distance in meters, and it's going to be a vector, right? Okay, so that's the definition of center of mass. Okay, so this was just the example I was giving. Now, so this is our position vector here. So here we're just considering in one dimension in x. So if we consider that the particles are moving, then we can also worry about the change in the position of mass, right? So if these coordinates are all changing, then if I sum up all the masses times the changes in the positions, that will give me the change in the position of mass, right? So just the same way, all I'm doing here is I'm just taking the deltas now, and I get the change in the position of the center of mass. So we can actually now calculate the velocity of the center of mass, because we can just differentiate that with respect to time. We've got a change in position divided by a change in time. And what we find is that the sum of the masses times the velocities divided by the sum of the masses gives us the velocity of the center of mass. And of course, this is just the sum of the momenta divided by the total mass. So if we take the sum of the momenta of all these particles, that will give us the velocity of the center of mass, right? So this is how we can see how the center of mass is changing. The position of the center of mass changes. Now, this is where we can do a neat little trick. If the velocity of the center of mass is the sum of all the momenta divided by the masses, then if we have a system where the sum of all the momentum is constant and does not change, then the velocity of the center of mass will not change either, right? Because if this is a constant value, then so will this be, and assuming we're not changing the masses, right? But if we're sticking with Newtonian mechanics, masses are going to stay the same. So, you know, if we sum up all the momenta of the system, and that's constant, then the velocity of the center of mass is also going to be constant. And so we can show this by going back to our example that we did with the golf club, right? Because in the golf club's case, we had two different types of collision, both of which the momentum was constant in. We had an elastic collision and an inelastic collision. And so what we can do is we can sum up the initial momentum beforehand and divide it by the total mass. And that's before the collision. We get the velocity of the center of mass is 16.7 meters per second. So this was the golf club head and the golf ball. And in the inelastic case, these were the velocities of the golf club head and the golf ball afterwards. And we can add this up to get the velocity of the center of mass, and we still get 16.7 meters per second. And in the elastic case, we can also do the same. We have to do this little extra calculation to get the velocity of the head, because we didn't calculate that before. But if we put that into our equation here, we still get the fact that the velocity of the center of mass is constant. And so sometimes it can actually help you solve problems if you know that the velocity of the center of mass before a collision is equal to the velocity of the center of mass after the collision. You can use that sometimes to get a bit of a shortcut. But we'll come back to center of mass when we start doing rigid body rotations. Okay, so we'll stop now, and I'll see you all on Monday. And we won't go, this will be the last material. Center of mass is the last thing that may appear on the midterm.